Welcome to the Wire Reinforcement Institute's Tech Check titled ACI 318 Welded Wire Reinforcement Tension Lap Splices. Tech checks are intended to provide specifiers, contractors, and other construction professionals with information needed for successful welded wire reinforcement implementation. So for this tech check, we'll start with an example project to set up some parameters that ultimately inform how the reinforcement can be configured to satisfy an engineer of record's design intent. With the criteria established, we'll then walk through 3 different welded wire reinforcement options. To wrap up, we'll do a side-by-side comparison of the 3 solutions. So for our example project, we define these requirements. We'll assume a 6-inch structural slab on ground, a 100,000 square foot building footprint. The engineer of record has prescriptively specified an area of steel of 0.17 inches squared per linear foot. Also has prescriptively defined a maximum and minimum spacing as noted, 10 inches and 4 inches on center. There is 1.5 inches clear cover from slab on ground top surface. We'll assume a steel reinforcement design yield strength of 60 KSI. The concrete design compressive strength will be F'C is 4 KSI. We're using normal weight concrete, and it will be required to have a Class B lap splice per ACI 318. So the welded wire reinforcement solution here would be a 10 by 10 D14.2 D14.2 for deformed wire, or a 10 by 10 W14.2 by W14.2 for plain wire. This 14.2 nomenclature simply corresponds to 0.142 square inches, and providing that at 10 inches on center gives an equivalent of 0.1704 square inches per linear foot, which of course satisfies the engineer of record's requirement. With the project parameters established, we'll look at our first reinforcement option, which is comprised of deformed welded wire reinforcement that is configured to achieve what we would refer to here as a coplanar lap. This simply means that the welded wire reinforcement mats, when installed, are able to occupy the same plane without stacking up or creating an unnecessary buildup of reinforcement. This type of lap splice is based on contribution from the deformed wire surface only, so there is no benefit derived from the welded cross wires themselves. In other words, and as we will show in subsequent slides, this lap splice ends up being calculated identically to that of individual pieces of rebar. If you look at the illustration here, note that the lap splice is intuitively measured as the overlapped horizontal distance from the end of one mat to the end of the second mat. Additionally, in practice, a welded wire reinforcement detailer will typically configure these mats to have overhang dimensions that allow for an uninterrupted typical spacing of the wires that are oriented in the direction perpendicular to the lap splice. So this ends up being really convenient for the placing crew, as there's no guesswork when it comes to laying out the mats. Basically, the overhangs themselves serve as a sort of built-in tape measure, and the final installed arrangement of the mats is able to maintain the typical spacing of wires throughout. The trigger for a coplanar lap splice can be seen in ACI 318 section 25.5.3. Looking at note A, we see that a traditional deformed welded wire reinforcement lap splice would require mats that stack in such a way so as to ensure that there is overlap of cross wires. In the absence of this overlap of cross wires, however, we're actually kicked to section 25.5.3.1.1, where we are directed to essentially disregard section 25.5.3 and head over to section 25.5.2. Section 25.5.2 covers lap splices for individual deformed bars or deformed wires. This actually should look fairly familiar. So what ACI is telling us is that if we don't have cross wires in the lap splice region of a deformed welded wire reinforcement mat, we derive lap splice length the same way we do for rebar. Since the original problem statement indicated that a Class B lap splice is required, we see here that our lap splice L sub ST will be the greater of 1.3 times L sub D and 12 inches. To find L sub D, section 25.4.2.1a applies. In section 25.4.2.1a, we are given a couple options. For this example, we're going to go ahead and use the expanded equation in section 25.4.2.4 to derive L sub d. And here is the expanded equation for L sub d, which should, again, look familiar to anyone who has calculated the development length for individual rebar or individual deformed wire. If we plug and play then, here are the applicable attributes, including the appropriate modification factors. Note too the calculation of the confinement term, which yields the use of the prescriptive maximum value in ACI that is noted to be 2.5. In equation form then, we arrive at L sub d equal to 9.68 inches. We can now calculate the Class B lap splice length. As shown, we arrive at 12.6 inches. We'll round this up to an even 13 inches for convenience. Wrapping up option 1, we show the actual configuring of the welded wire reinforcement mat and its representative quantity takeoff. We're going to assume that for this project, and as a function of an agreed upon preference between the welded wire reinforcement manufacturer and the contractor, that the mats are going to be on the order of about 20 feet long and no wider than 8'6". So the 8'6" maximum width is notable because it represents the maximum width that can be carried by a standard truck before additional oversized load permit requirements are invoked. With all that said, note the resulting mat style here. One of the overhangs is equal to the calculated lap splice length of 13 inches, while the adjoining overhang that will be overlapped is 10 inches long. This yields an effective mat coverage of a little over 122 square feet, with effective coverage indicated by the dashed line. So the result for a 100,000 square foot slab is a gross area takeoff that gives us 819 mats. This equates to about 65 tons of steel, and these results will be revisited later as part of a comparison between the other two options. Moving into option 2, we have deformed welded wire reinforcement in a stacked lap splice configuration. The key attribute to be aware of here is that the calculation of the lap splice is based on both the deformed wire surface and the presence of welded cross wires within the lap region. As you can see, if welded cross wires are in the lap splice region so that they can be relied upon to contribute to the bond and anchorage, we end up with an unavoidable stacking of the mats where they come together. It's just something to keep in mind. Revisiting section 25.5.3, and with the benefit of the illustration shown, we see that both conditions A and B are satisfied. So in doing so, ACI tells us that the lap splice length will be the greater of 1.3 times L sub d and 8 inches, with L sub d calculated in accordance with section 25.4.6.1a. Section 25.4.6.1a kicks us into section 25.4.6.2 for the determination of L sub d. The next step is nearly identical to what we saw in option 1 for the coplanar lap splice, in that we will be relying on section 25.4.2.4 again. However, there is one significant difference, and that is the application of a deformed wire reinforcement factor as outlined in section 25.4.6.3. So if we put this all together, we have the familiar expanded development length equation of section 25.4.2.4 multiplied by the deformed wire reinforcement factor of section 25.4.6.3. Here we walk through the attributes of the development length equation. This part is actually identical to that which we had derived for option 1 previously. But we now take the result of that equation and multiply it by the deformed wire reinforcement factor. This ends up giving us an L sub d that is equal to 4.03 inches. Circling back then, we can now calculate the lap splice length as the greater of 1.3 times L sub d and 8 inches. We see clearly here that 8 inches governs. In configuring the lap splice itself, we need to ensure that there is the prescribed minimum overlap distance from the crosswire of one mat to the crosswire of the next. Here we elected to provide a 6-inch overlap between these crosswires, which, when coupled with 1-inch overhangs, achieves our required 8-inch lap splice dimension, as well as the prescribed 2-inch overlap of crosswires therein. Notice again the inherent stacking of the mats due to the required presence of the crosswires within the lap region. So while this lap splice length is certainly shorter than what we calculated in option 1, not only is there some material buildup to be aware of due to the stacking, but there is also a bit of a disruption to the regular cadence of the typical reinforcement spacing that occurs everywhere else on the mats. This, of course, isn't impossible for the contractor to achieve in the field, but it does require a bit more attention to detail than in option 1, where we could simply use the overhang length as a sort of built-in measuring stick. And here we see the culmination of the efforts for option 2, arriving at a mat style with coverage that is a bit more than 146 square feet. Again, effective coverage is indicated by the dashed line and is based on the overlap relationship we showed in the previous slide. From here, we derive a mat quantity and corresponding steel tonnage as representative of a gross area takeoff. You can see that the mats are fewer than what we derived from option 1, and the tonnage is actually a little bit higher. It is worth pointing out that if you are going to rely on the presence of welded crosswires within the lap splice region to contribute to bond and anchorage behavior, you must also satisfy a prescriptive maximum wire spacing throughout the balance of the mat's area. And this is noted in ACI section 20.2.1.7.3. This prescriptive maximum spacing is 16 inches. Of course, we've satisfied this given that the mat we have configured here has a 10-inch wire spacing. Again, this prescription only applies when there is contribution from welded intersections being relied upon for the bond and anchorage of the mat. In contrast, for option 1, that we previously derived based entirely on anchorage and bond contribution from the deformed wire surface only, section 20.2.1.7.3 does not apply. We'll now move into our final option, which is comprised of plain welded wire reinforcement. For this lap splice, the bond and anchorage behavior is entirely reliant on the presence of welded crosswires. This is because the wire surface is smooth and as such cannot contribute to bond or anchorage. Note that the lap splice dimension is measured from outermost center lines of crosswires on the lapped mats, independent of overhang, and there is an additional implicit requirement that a 2-inch minimum offset be achieved. We can see here that there is a significant departure in the ACI design routine for lap splice calculation, and that it doesn't really resemble the equations we saw in options number 1 and number 2. Section 25.5.4.1 applies here since the ratio of steel area provided to steel area required is less than 2. Section 25.5.4.2 is also shown in brackets at the bottom, but it doesn't really apply to our example. Note the 3 different provisions listed as A through C, the greatest of which will be used as the tension lap splice length. Provision B tells us to go to section 25.4.7.2b for the determination of L sub D. When we arrive there, we see a fairly straightforward equation, the result of which is 3.64 inches for the problem statement that we're working here. So lap splice length is the greatest of spacing plus 2 inches, which would give us 12 inches, 1.5 times L sub D, which gives us 5.46 inches, and a prescriptive value of 6 inches. So our lap splice length is 12 inches. With the lap splice length in mind and the requirement that we have a 2-inch minimum crosswire offset requirement that we need to satisfy, we configure the lap splice that we show here. Note the 12-inch measurement wire to wire and the 2-inch offset that is integral within that region. While we've arbitrarily selected a 1-inch overhang here just as a representation of a practical minimum for manufacture, these overhangs could be longer. At 1 inch, note that the overall mat overlap dimension ends up being 14 inches. But again, this end-to-end dimension does not represent the actual lap splice dimension. The lap splice is the 12-inch dimension from outermost crosswire to crosswire. Generally speaking, for plain welded wire reinforcement, overhangs that occur to the outside of the lap splice itself are structurally irrelevant, and they offer no benefit in the calculation. That said, from a reinforcement placement standpoint, it still might be prudent for the designer on their construction documents to speak in terms of mat overlap, as this could make the task of the sheet layout simpler for the contractor to keep track of from one mat laydown to the next. Finally, note that this type of lap splice is also characterized by an unavoidable stacking of the mats given the required cross wires positioned within the lap region. Here is the culminating information for option 3, with mat quantity and steel tonnage representative of a gross area takeoff. The dashed line represents the effective coverage of a typical mat, coming in at a bit more than 133 square feet, and derived based on the lap splice configuration shown on the previous slide. Similar to option 2, anytime welded wire intersections are relied upon for bond and anchorage, other than those used as stirrups, ACI requires that there be a prescriptive maximum spacing of wires throughout the field of the mat. Here, for plain welded wire reinforcement, that prescriptive maximum is 12 inches, which we of course satisfy with the 10-inch spacing shown on the mat that will be used. In wrapping up then, we summarize the three options here. Steel tonnage-wise, the coplanar lap solution for deformed welded wire reinforcement will always be the most efficient, given that longer lap splice lengths still comprise less steel weight when compared to that associated with additional cross wires positioned within a shorter lap splice region. Of course, those additional cross wires occur for option 2 and option 3. Additionally, for the deformed welded wire reinforcement coplanar lap, the added benefit is that all of the steel remains in the same plane, so there's no buildup that can potentially affect steel positioning within the depth of the concrete element. This is by far the most preferable arrangement from a design perspective. The one trade-off for the deformed coplanar option is that there is obviously a larger quantity of deformed welded wire reinforcement mats, but keep in mind that these mats are lighter. Each one of them's 150 pounds each, and that's in comparison to the other two options where the mats weigh at about 200 pounds each. So the increased quantity coupled with the lighter mat weight ends up likely being somewhat of a wash. Overall, the takeaway is that while all three options are viable solutions and are code compliant, the deformed welded wire reinforcement option with coplanar lap splices is generally considered to be the most cost and labor efficient solution of the three, and is preferable from a design perspective. For a bit more information on welded wire lap splices and takeoff comparisons related to time and labor economy, take a look at the WRI's online technical blog library. The WRI actually published a blog specific to this topic back in November 2022 that will prove useful. Thank you for watching this WRI Tech Check. Please don't hesitate to visit the Wire Reinforcement Institute website for more technical information.